Okay, we're going to continue on here talking about titrations here. We are almost to the end of chapter 14, believe it or not. I can't believe it. All right. So we last time talked about a couple of titrations, and lastly, we focused on the weak acid, strong base titration. And again, in this titration, you are adding your base from your burette. You have your weak acid there in your beaker or flask. And again, that does give us a titration curve that looks similar to the one we saw with strong acid, strong base. So it's kind of S curve here. We take pH versus volume of base added. And remember, pretty much on all titration curves, or titrations really in general, there's really kind of four parts that we sort of concern ourselves with. And the first part there is before we begin the titration. And as we talked about last time, before we begin the titration, really the only thing that we have present is the weak acid, which means that because it is a weak acid, you will need to do an ice table. And again, this can be done in molarity as you haven't added any base or anything like that, so there's no volumes changing. And basically, you're going to solve for X. And again, X in this case will equal your H plus concentration. And then you basically could go into your pH at that point. The sort of second part of the titration that we're usually interested in is before the equivalence point. So obviously before the equivalence point, you are adding base in this particular case. So this does require one ice table at least at this point because we are adding volume. We do need to do this in moles at this point. You should, as usual, after you do that first ice table, then convert it back to molarity using your total volume that you added. What you should always end up with in this type of titration before the equivalence point is essentially you should always end up with a buffer. And you should really pretty much end up with a buffer at this point. And that does give you sort of a choice as to what you do after the first ice table. Probably the best move there is going to be your Henderson-Hasselbalch equation, since it is a buffer. You again could also do a second ice table if you wanted to. But really the purpose of the first ice table is to figure out the concentration of the buffer that you made. And then you could obviously solve for it like a buffer problem. The third part of the titration curve there occurs at the equivalence point. And when you're at the equivalence point, you do again need to do an ice table here in moles, then converted to molarity. And because the equivalence point is the point where the moles of the acid and base basically equal each other, you basically will have only a salt sort of left over at that point. That salt, because it did come from a weak acid, will go through hydrolysis. So this point in the titration curve, it's going to be a second ice table you got to do there. And that's going to be a hydrolysis ice table where the salt will react with water, and it will react with water as a base because it comes from an acid. And that means it will actually accept the H plus from water. And the result of that is you're going to produce hydroxide, and it's going to be basic, this pH here at the equivalence point in this type of titration. Again, because you always will have this salt that came from a weak acid, it will always go through hydrolysis and it'll always basically produce that. So that's sort of a double ice table situation there at the equivalence point. The first one really, again, in this case, is actually to figure out the concentration of your salt that you got. And then the second one really is just like a hydrolysis type one that we did when we talked about salts. And that will get you your pH. Again, you should always really probably hit basic at this point at the equivalence point, which again is different than a strong acid, strong base where it will be neutral. And that is because in that type of titration, the only salt you have left is a neutral salt, something like sodium chloride, for example, that will not go through hydrolysis. The fourth part here, once again, now you're going past the equivalence point. So like normal, we got to do an ice table in moles, then convert it to molarity. At this point, you basically have two things left over. You do have the salt that was there from the equivalence point on, and that salt obviously is going through hydrolysis like we just talked about. But more importantly, in terms of the pH, what you have at this point is pretty much this guy. You're just like dropping in the base like there's no tomorrow. And that's going to be the major contributor basically to the pH. So you really will have a strong base left over at this point. That will give you the OH minus concentration. And obviously from that, you can get yourself to the pH by going POH and then pH at that point. So again, the graph sort of looks similar to what we saw with a strong acid, strong base. But again, because there is a weak acid sort of in this titration, the way that we got to calculate the pH at different parts is different. It's basically good news, kind of all the calculations we've done before. Again, the hard part for a lot of people is applying it correctly. So at the very beginning here, it's basically just a regular old weak acid Ka type problem. Before the equivalence point, it's basically a buffer problem. At the equivalence point, it's a hydrolysis problem. And past the equivalence point, it's basically a strong base problem. Any questions on any of that there? All right, then let us talk about the next type of titration. And this is a titration of a strong acid with a weak base. And it's a little bit different looking, as you can kind of see from the graph, than the ones we saw previously. So we could take a strong acid like hydrochloric acid, and we could react it with a weak base like ammonia, and we will get ammonium chloride. And I'm actually going to separate them, and I'll talk about why I do that in a second, but you could also keep them together as NH4Cl as well. So you could kind of separate them or keep them together in this particular case. In this case, though, the way we're doing this is up in the burette is actually the HCl. Down in the beaker or flask to start with is actually your NH3. So we're actually adding acid to our base in this case. So again, a little bit different than what we see. We actually see, because of that, the curve's like upside down, if you will. We're actually starting at a high pH and we're ending at a low pH because we're actually adding acid in this case. So we're going to start high because we're starting with the base. As we add the acid, the pH is going to start to drop. So it's kind of like the other ones, just starting in the opposite direction and working our way down. There is still the same really 4 parts of this titration curve as the others. Again, really before we begin, before the equivalence point, at the equivalence point, and once again, past the equivalence point. So just like we did with the other ones, we're going to talk about sort of what's happening at each of these points. So hopefully you'll understand what's going on. So let's start with the first part there, which is obviously before we start the titration. Now, since this is before we start the titration, in this particular case, again, the setup is we're actually adding the acid to the base. So really the only thing that we have kind of in the beaker or the flask before we start the titration is a weak base. So we basically have just a weak base. That means that this is really just a KB type problem where we would take our weak base and we will have it kind of do its thing. And remember, when you have a base, probably you should include the water. And again, it's going to accept the H plus. The result of that is you'll make NH4 plus and OH minus, which once again, you could keep it together or break it apart. And in this case, this is just going to be a regular ice table. We could use molarity here because again, we haven't started the titration, which means we haven't added any volume. We could do our zeros, our minus X's, plus X's, plus X's. And obviously like a normal table here. This would go once again into our KB as this is a weak base, and we would solve for X. We do want to remember that this is a base, so when we actually do solve for X in this case, it is not the H plus concentration, but it is the OH minus concentration, which means then that we got to do probably a little POH first and then to the pH. So similar to what we saw in the previous titration curve where we had a weak acid, in this case we have a weak base, and again just a basic sort of KB problem like we did at the beginning of this chapter. way back whenever we started this chapter, seems like forever. And you just basically solve for the pH. Any questions on that there? All right, then let's talk about the second part of this. And the second part of it obviously is before the equivalence point. So again, we are actually starting our titration here. So as step number 2, we are before the equivalence point. So at that point, obviously, we're going to get a reaction between our acid and our base in this case. So we'll have our equation here, a little HCl, again with some our weak base here, our ammonia. Again, it's going to accept the H plus in this case, gonna make ammonium chloride basically. And here we go. So obviously here we do need to do an ice table, and it does need to be done in moles. In this case, we are starting with this guy and we're actually adding the HCl. So I'm going to start with, again, that made up number 4 like we've been using in these examples here. So once again, as we've talked about previously, since we are before the equivalence point, the moles of whatever we're adding should be less than what we started with, right? Again, the equivalence point means that they are equal to each other. So obviously we would have it below that. So we'll start with 2 moles here, and we'll have 0 here. Change is going to be -2 and -2, as again here what we are adding is the limiting reagent. The excess reagents are really base in this case because we've got plenty of moles of it. This will give us 2 moles in this case. At equilibrium here, we'll have nothing of what we added because it's a limiting reagent. We'll have 2 moles of this guy and 2 moles of this guy. I obviously also want to do really good practice like we talked about. We again want to use our total volume here, right? Convert it to liters to convert these guys back to molarity. As I mentioned a number of times, and a lot of calculations, you really kind of need molarity to kind of continue on with the calculation if you kind of want to get it correct. So it's just really good practice after that first IC. We'll just kind of convert everybody back into molarity. Now you may be wondering, and why I didn't put anything here. Why did I not put anything there? Chloride is what type of thing? It is neutral, right? So if we already know it's neutral, not going to do anything with the pH, perhaps a good idea not to put any numbers that you're going to want to use wrongly in your calculation, right? So we don't really have to worry about the chloride in this particular case. Again, because it really comes from this guy here, right? So it comes from something that is strong. So it will be basically neutral. It will not go through hydrolysis or anything like that. So once again, if you're not sure what's going on at this point, you should always look towards your ice table to help you figure it out. And really what we got left is this guy and this guy. And once again, hopefully you could recognize that they are related to each other. They're basically related to each other by 1H plus. That's a weak base and its conjugate acid. They also call that still a buffer, right? So again, this is an example like we saw in the previous titration that you can actually make a buffer from a reaction of a strong acid and a weak base like we just did here. Once again, the buffer is not the strong acid part of it. It is actually the products that are made at the end of that reaction, and the strong acid is actually gone, and we did make a buffer. So once again here, we hit buffer territory. So I would again recommend probably the Henderson-Hasselbalch equation. Less room for error, but if you want to do an ice table instead, you absolutely can. In this case, you have actually a couple options. If you choose the ice table approach rather than the Henderson-Hasselbalch equation, you could actually do like a KB type of situation here with the NH3. You could also get the Ka value from the Kb value and do a Ka type calculation with NH4 plus. So you have a couple of options as to how you want to do that. Or again, you can use your Henderson-Hasselbalch equation. So much like we saw in the previous one, we will create a buffer in this case. It's actually a basic buffer because most of the way, because again, what we're starting with. So we will get some buffering action that's going to happen. And again, the same idea here as we've been talking about previously in the last one. At some point, you'll make this buffer, and then you'll basically blow through the buffer you just made there. And again, much like we saw in the previous titrations where the pH kind of jumped up to the equivalence point. In this case, we'll actually see the opposite. It's going to drop pretty dramatically as you go to the equivalence point. And again, this is because you just blew through your buffer and you're adding more acid, right? So you're going to have a big influx of H plus into the solution really quickly. And that's going to cause that kind of big actually drop in the pH to the equivalence point. It's basically the same idea as when you hit it with the base, you get the big influx of OH, which makes the pH jump up to the equivalence point. So again, that's what we see happening. We also see again a kind of vertical drop here. So once again, much like we saw in the other titrations, as you typically approach the equivalence point, it does not take a lot of volume to change the pH a lot. And again, that's why when we use something like indicators, we sometimes can see a big change in the color with not a lot of volume of whatever you're adding when you add it to it. So let's talk about what happens when we do hit that equivalence point now that we kind of made our buffer and then blew through our buffer. So at the third step here, we're going to be at the equivalence point. And once again, we definitely are adding if we're at the equivalence point here. So we'll have our reaction here of our hydrochloric acid plus our ammonia, giving us our NH4 plus and our Cl minus. And in this case, since we are at the equivalence point, once again, we're adding this guy. We are starting with this guy here. And we'll use our 4 moles here of what we're starting with. So once again, our definition of equivalence point is we should have equal moles at this point. So that's going to be a 4-pack there of moles for the HCl and a 0. Once again here, you can't really hopefully mess up. You're going to end up with a -4 since that's the only number present. And once again here, 0 and 0. And that is typically what we do expect to happen at the equivalence point of our titration. We should basically have used up all of our reactants. So this is essentially why we typically in a normal titration that you do stop at the equivalence point, right? Because technically the reaction is kind of done in a sense. So that's usually why we want to kind of stop at that point. Here we have 4 moles. Once again, we will convert this using our total volume back into molarity. And at this point, if you're not sure what's going on, you can see what we got left. We obviously have some NH4 plus left. Technically speaking, we do have chloride left. And again, for the same reasons, because that comes from a strong acid, we're not going to really worry too much about it. Once again, here you could keep the ammonium chloride together and just have one thing on the product side, which would be the ammonium chloride. So that's okay too. You just have to do the next step of realizing the chloride part's not going to do anything, obviously, as well. So if you kept those guys together, you just got to think of it as basically the salt that is left over. And again, you should hopefully be able to analyze that the chloride won't do anything. But now when we do come to the salt part here, that is the NH4 plus, as we talked about, it does definitely come from this weak base, which means this is going to be a conjugate acid that will go through hydrolysis because again, it comes from a weak base, right? So anything that comes from a weak acid or a weak base will go through hydrolysis and react with water. And that's essentially what's going to happen. So in this particular case, we will have really from the salt, only the NH4 plus part. Once again, our true salt here is ammonium chloride. This part not going to do anything. It's going to react with water and do a hydrolysis problem. Once again, because it comes from a base, it will act as an acid in this case, which means it's actually going to send the H plus over to the water. And when it does so, we once again, as we've talked about a number of times, will produce where that salt came from, which is ammonia. And it will produce H3O plus in this case. And because it will produce H3O plus, we should automatically know that this solution at the equivalence point should be acidic, as we will have H3O plus being produced. This will then be an ice table, and really the purpose of the ice table, the first ice table, is to get this guy's concentration so that now it can be your initial down here. And again, this is a point where you definitely want molarity and not moles. So as I mentioned before, just convert it back to molarity all the time after that first ice table, and you'll usually be in the good shape in terms of the units that you need. If you roll into this table with moles, you'll get the wrong answer if you don't adjust for it later. So again, it's a good idea to always convert it. So we'll do molarity, and really because we're kind of doing molarity here, this is then going to be a table with X's. And most of the time that is the case. Not all the time, but most of the time that's the case. Got molarity, you can probably have X's. The other thing that we also want to think about here is when we put this into our K expression, this should be a Ka once again, because we are producing H3O plus. Once again, on this type of problem, you probably will have the KB value given to you. So again, you got to use that KW equals Ka times Kb to switch it over there. Again, the Kw, the normal number there, 1 times 10 to the minus 14. Once you do that, you will obviously solve for x, however you want to do that, which is probably an assumption. And actually, in this particular case, though, the x does actually equal the H plus concentration, which means you could go directly into your pH equation and actually solve for it. So very similar to what we saw in the previous titration, when you reach the equivalence point, you are going to need 2 ice tables because basically you will have a salt that will go through hydrolysis. That salt, because it always comes from a weak base, will also go through hydrolysis and always produce H3O plus, and it will always be acidic at this point. And that's how come we know when we take a look at the equivalence point in a titration of a strong acid and a weak base, we should hit a acidic pH basically in this case. Any questions on that there? All right, so you hit the equivalence point, your indicator changes, but it doesn't stop you. You keep titrating. So we go now to the fourth part here, and that is definitely after the equivalence point. So clearly we're still titrating here, so we'll do our equation again. And once again, this is what we started with, and this is what we're adding. So we're going to start with our 4 moles here. And at this point, we are definitely past the equivalence point. So our moles, as we talked about previously at this point of what we are adding, should be more than what we started with. So again, I'll just make up the number of 6 moles in this case, and that's going to give me a 0. At this point, again, there's that switch that occurs where what we're adding now becomes the excess reagent, and what we started with becomes now like the limiting reagent. And that means always, as we talked about, you want to take the smaller number. So the change here is actually going to be the base. And that is going to give us here 2 moles of this guy, 0, and 4 moles of this guy. Once again, good practice here, converting back to molarity using our total volume at this point. So at this point, if we take a look at it, we got a couple of things left over. Obviously, we're still not concerned about the chloride at all here and here. Once again, hopefully you know that these two things are not related to each other. So again, this is not a buffer. HCl and NH4 plus is definitely not a buffer for sure. And you should not use the Henderson-Hasselbalch equation here. And that's a very common mistake. Like I said, probably a number of times, people get to this point, they have 2 numbers, and they think, that seems like a good equation to use since it requires 2 numbers. So remember, only in a buffer situation, which this is not. So we basically have this acid, which is basically a salt, and it will behave like an acid, which means it will produce H3O plus, right? And it will go through hydrolysis, basically. But in addition to that, though, we also have HCl, which is definitely a strong acid. So what we essentially have is kind of like 2 acids left over at this point. And between the two, the HCl is definitely much, much stronger than the weak acid there of NH4 plus. That NH4 plus has got to go find some water, right? Do a little reaction to produce some H plus. The HCl pretty much just needs you to drop it into the flask and go for a swim, and it's going to break apart completely and produce H plus really quickly. So at this point in titration, much like we saw in the last one, we're actually going to ignore the contribution of the salt because it's not going to be the major contributor to the pH in this case, and that's going to be the HCl. And the HCl, because it is a strong acid, means that you pretty much have the H plus concentration, which is what we got there. And because of that, you could go right into the pH equation at this point. So it's really a strong acid type problem at this point, and you could go right into the pH equation because of that. Any questions on that? So what we see here really is pretty much very similar to the previous titration we talked about with a weak acid and strong base. You have, in this case, because we're starting with a base, really a KB type problem at the beginning, you're going to hit a buffer there before the equivalence point. As we saw there, you'll have a little hydrolysis with the salt happening that will always become acidic because it comes from a weak base, and you basically have a strong acid problem there at the end. Any questions on that one there? All right, so why don't we try one here? Let's see, let's do let's do what is the pH after 27 milliliters of 0.1 molar HCl is added to 25 milliliters of 0.1 molar NH3? Do that. The KB for NH3 is 1.8 times 10 to the minus 5. All right, give it a go, see what you come up with there. Trading, so we need some moles of everybody, so might as well start with that. So we'll do our moles of HCl. That's going to be, again, we want to convert our volume into liters, times it by the molarity here. And that's going to get us there. Looks like 0.0027 moles of HCl. We'll do the same thing here for our NH3. We have 25 mils, which 0.025 liters, times the molarity, 0.1 moles per liter. And again, that's going to give us something similar there. 0.0025 moles of NH3. So again, with our equation here, HCl plus our NH3, going to give us our NH4 plus our Cl minus as well. Again, we are starting with this guy. We are adding this. So initially we have 0.00270 moles. We have 0.00250 moles and 0. Am I before, at, or after the equivalence point in this case? I am after, because what I'm adding is more moles than what I started with. So again, we are after the equivalence point. Again, taking that moment to figure out where you are in the titration curve can help you do the math correctly, because now you really should know what should happen. And at this point, since we're past the equivalence point, we're pretty much just dropping acid right at this point in there. So we basically have a strong acid problem that should happen. So sometimes it's better to know what calculation you should do before you start the calculation, right? Or have directions than just to start driving around streets trying to find where you're going, right? Even though you say, I know where I'm going, right? You eventually get there, but you might get lost along the way, right? So it's good to kind of know what you want to do before you start. Because we are past the equivalence point, we know this is our limiting reagent now, and this is our excess reagent. But even if you didn't know that, you should always know the smallest number is the choice there, so you do not end up with a negative. So we want to go again with our smallest number, which again, in this case, is our base moles here. That's going to get us here 0.0027 minus 0.0025. That's a lot of zeros, 0.0002 moles. That's going to be 0 and obviously 0.0025 moles. We again want to always convert things back to molarity after this first table. So obviously we started with 25 milliliters. We added 27 milliliters of our base. And that is we got there 252 milliliters, I think. So our total volume there gonna be 52 milliliters. So we want to divide it, converted it to liters. So 0.0520, 0.0520. That will get us back into molarity at this point. It's going to give us a 0.003846 molar and a 0.0025 divided by 0.0520. 0.04808 molar. First off, any questions on the table here? So again, if you're not sure what's going on, you should always look at your ice table. It could give you a lot of information. So clearly here we know from our conversation, we're not worried at all about that guy. Here we have this guy left over and this guy left over. And as we were just talking about a second ago, again, this is not a buffer. So just because you have two numbers, you should not throw it into the Henderson-Hasselbalch equation. This is the part, as we know from just knowing where we are in the titration curve, we are adding excess amount of acid. So we have a salt that will go through hydrolysis that's going to act as an acid, but we definitely have our strong acid here, right? And that is going to be our major contributor at this point. And this is the point of the titration where we do ignore the contribution of the salt. And because of that, this is actually going to be our H plus concentration. And that means we could go right into our pH here at this point. And it's that number there. Maybe a 2.41 pH, which does sort of make sense since we are just adding excess amount of acid. So we should expect obviously the pH to be acidic in this case. Any questions on that there? And see how we did here since this was this titration here. So 27 puts us right there. That's between those two numbers. So that's pretty good as well. Question on this type of titration here, strong acid, weak base titration. All right, well, work on at these 4 different spots along this titration. Again, reminder that typically speaking, when you do titration problems like this, where you have multiple sort of spots, the volume doesn't like continue over, if that makes sense. So what you think about is like on part A, you just open it up to whatever you needed, shut it. For part B, you start it at 0 again, open it up to that point and shut it. So it's not like a continuation type of calculation using the volumes or anything like that. So it's assumed that you're just kind of stopping for the beginnings part and each or starting at the beginning from each spot there in this titration. All right, so give it a go. We got 100 milliliters of 0.1 molar nitrous acid titrated with 0.1 molar sodium hydroxide. We're looking for 4 pHs here. What's the pH of the initial solution? What is it after we add 80 milliliters of base? What is it at the equivalence point? And then what is it after we add 105 milliliters of the base? The Ka there for nitrous acid, 4.5 times 10 to the minus 4. So give it a go, work it out. And we'll start talking about it in a while here. Okay, let's take a look at least at the first part here, since you hopefully should got through that, I would hope. So start with this titration here. So a good idea is to think about what type of titration we're doing. So obviously we have nitrous acid and sodium hydroxide. I know nitrous acid is a weak acid. And I know that for sure because I see a Ka value for it down there. So that's a big old hint. Sodium hydroxide is a strong base. So we're doing basically our middle titration we talked about there of a weak acid and a strong base. And again, that should give us some type of curve that looks something like that as we go through there. So clearly here in part A, that's the initial solution. So that is way back here, step number 1 that we've been talking about. Again, we are adding, in this case, the sodium hydroxide when we are doing the titration, and we are adding that to our weak acid here. So we're adding our base to our acid. So initially, really the only thing that we have there in the beaker or the flask is our weak acid. So as we know, this should be just a regular old sort of Ka type problem. Again, we could do it in molarity as we have not added any base at this point. So for part A here, I believe it was 0.1 molar, if I'm not mistaken, 4.5 to the -4. So we have our Ka value, and we basically have at this point 0.1 molar nitrous acid. So again, weak acid, so definitely need a nice table here. So we're going to do our weak acid breaking apart into its ions here. That's going to give us a Ka expression here of our products over our reactants. And again, that's going to equal our Ka value there, 4.5 times 10 to the -4. So starting here, we have 0.1 molar. We have 0 and 0. Change here going to be x's. And at equilibrium, 0.1 minus x, x, and x. Any questions on the table here? So like normal, just a regular old sort of K problem, basically. We're going to take our equilibrium line and go in there. So that's going to give us basically x squared divided by 0.1 minus x equals our Ka value of 4.5 times 10 to the -4. Now you can assume just like normal and make an assumption that x is equal to 0. And hopefully, like normal, you actually checked it and saw it was a bad assumption at 6.7%. So if you did the assumption, hopefully you checked it. If you didn't, you should have checked it because it is more than 5%, and you cannot use the assumption in this case. So a good reminder, you should always check your assumptions when you do them. And again, to check your assumptions, you would get your x value and divide it by basically what you're going to subtract it from, times it by 100, and you should hit 6.7% in this case. So this means good old throwback quadratic day. Is that we're going to move that way here. And that's going to get us 0.00045 minus 4.5 times 10 to the -4. We want to bring everybody the same side. That's going to give us x squared, actually plus 4.5 times 10 to, then there should be an x there, I think, minus 4x. And then we're going to subtract that other guy there, 0.0000045 is equal to 0 in this case. That is going to get us our quadratic A, B, and C. Again, that's going to go into x is equal to minus b plus or minus the square root b squared minus 4ac divided by 2a. Popping in our numbers there is going to get us a negative 4.5 times 10 to the -4 plus or minus. If you do everything inside the square root, you should get something like 0.0001802. And then if you square root it after that, you get 0.01342. That's all going to be divided by 2a, which basically is 2 in this case. This is again going to give us our two values possible here. Going in the plus direction there, it's going to get us a x value of 0.006485. Going in the negative is going to give us a negative value of negative 0.006935. So clearly in this case, since we do need our H plus, and we can clearly see from our table that this equals X, negative is no good here. So that should then be our H plus concentration in this case. And now we have the appropriate H plus concentration to go into our pH. And our pH here is minus the log of the H plus. And that's going to give me minus log of 0.006485. And that is going to open us here on the titration with an opening pH of 2.19. Yeah. Now, if you did the assumption, you actually got a pretty close number because it's only 6% off, which is pretty close, but not the right answer, just so you know. Yes, any questions on that there? All right, that is part A. Let's then talk, hopefully got into B as well. So we'll take a look at B here to finish it out for today. What is the pH now that we've started the titration and we're going to add 80 milliliters of our base to it? So obviously here we are starting our titration. So that means we do need to do moles. So we're going to do 80 milliliters of our 0.1 molar sodium hydroxide. And we're going to add that, I think it was 100 milliliters, right? Yeah, 100 milliliters of our acid there to 100 milliliters of 0.1 molar HNO2, and our Ka still 4.5 times 10 to the minus 4. So obviously we are going to be adding, so we need some moles, so why not start there? So we'll go moles of our sodium hydroxide here. Again, we got to convert our volume into liters, so everything cancels out correctly. We'll use our molarity of our base, and that's going to give us for our sodium hydroxide 0.008 moles. We'll do the same thing here for our acid, 0.1 liters times the molarity there, 0.1 moles per liter. And that's going to get us there 0.01 moles in this case. So we'll do our reaction. We're going to take our nitrous acid there, going to react it there with basically sodium hydroxide. Going to do a little double displacement reaction, going to make a little NaNO2 and a little H2O here, right? As basically these two guys switch partners, right, as we go across. So clear, we're going to do this in moles. And if we take a look at what's going on here, get rid of that there, maybe. Again, this is what we started with. This is what we added or are adding. And in this particular case, then we have 0.01 moles and 0.008 moles and 0. So am I before, at the equivalence point, or after the equivalence point in this case? I am before. What I'm adding is less than what I started with. Not to mention the next part of the question is what's the pH at the equivalence point? So I'm probably before it, but this is really how you could determine. So we definitely are before the equivalence point, which means in this type of titration, we should end up with a, well, if you're not sure, I guess we'll figure it out in a second, I suppose, right? So we should already know where we should end up. Let's see if we do end up there. So at this point, it is a limiting reagent. This is our excess reagent. So we can go with a smaller number here, 0.008 minus 0.008 and plus 0.008 moles. That's going to get us here at equilibrium, 0.01 minus 0.008. 0.002 moles, 0 that guy, 0.008 moles of this guy. Again, we want to convert back into molarity. So we started with 100 milliliters of our acid. We added 80 milliliters of our base. That's going to give us a total volume there of 180 milliliters. That means both of these guys get divided by 0.18 liters. And we'll go 0.002 divided by 0.18. Going to give us a 0.0111. Lots of ones. 0.008 there divided by 0.18 there. And a bunch of fours to match it on this side. There we go. So again, at this point, if you're not sure, which you should really be sure before you started, by the way, you have this guy and you have this guy. Again, they are related to each other. This again is a buffer, which is what we should expect to occur at this point in the titration, even before we did the calculation, by the way. So that's a good thing again to know. So because it is a buffer, why not use our buffer equation, do a little David Hasselhoff equation here, a little pKa plus the log of the base divided by the acid. That means we do need a pKa value. So we'll get that by taking minus the log of the Ka. It's going to go minus log of our 4.5 times 10 to the minus 4. 3.35 looks like. So 3.35 plus the log. Again, we want to make sure we get our base up there on top. Since that is the acid, it also has one more H plus. Our base typically will have a spectator ion like a sodium. So that's going to be 0.0444 up on top, 0.0111 on the bottom. 0.0444 divided by 0.0111. A little logage action there of 3.35. And at this point, we are now at a 3.95 pH, which does make sense since we started at a 2.19. We added 80 milliliters of base. We